welcome Surya. It's a pleasure to have her. So she was actually supposed to speak a year ago, just before all hell broke loose, and we've kept rescheduling, and hopefully she'll visit another time. Surya is a research scientist, a senior researcher at Microsoft Research, and before that she was a research assistant professor at TTI, and she is well known to many of you for her fundamental work on algorithmic regularization, or implicit bias arising from optimization methods and different architectures. She also worked on different biases, with the bias that comes from discrimination and making algorithms fair. And today she will work on the she'll talk on the algorithmic bias. Just take it away.
Thanks, Atal, and thanks for inviting me. And it is really a pity that I couldn't be in person. Like, I was looking forward to the East Coast trip for various reasons. So today I'll talk about what we call as like the function space view of certain types of regularization, specifically L2 regularization of the parameters. So this is in some sense complementary to the other line of work I've done on implicit regularization or algorithmic regularization, and I'll make the connections towards the end of the talk. So like I was saying just before starting, like I didn't realize that my co-author Meena gave a similar talk just a few days back, I think on Wednesday in a computer science seminar. So I apologize if there is too much overlap, but I am going to try to make at least half of the talk non-overlapping, so I can talk a bit more about the connections to algorithmic regularization. In the first part of the talk, I'm going to give like results where you can think of the results as something independent of independent of even learning and data. And the second half is where I'll make the connections to where learning comes in. So this is joint work with Meena, who's the primary author on this paper, and Ilya Stein, who was my colleague and is currently doing startups.
Okay, great. Okay, so like I was saying, this is joint work with Meena and Ilya. So to set up the problem a little bit, we give a little bit of motivation before we set up the problem. The context for learning this, studying this problem is in learning prediction function, where we have an input x and a label y, and we want a function which maps inputs to something which is indicative of the labels. And a large class of these prediction functions involve considering a family of functions which are parameterized by some tunable parameters w. And the key component of learning process involves like some form of loss minimization, where we tune the parameters towards minimizing some predefined loss over a predefined data set. And usually in learning, the goal is to have good performance on new examples. And traditionally, if you have a number of parameters which is much less than the number of examples, you can achieve this goal by like simply invoking like Chernoff bounds and of large numbers and so on. But today we'll be focusing on settings which are called over-parameterized model, where usually like the number of tunable parameters is much larger than the number of examples. So again, like I said, the learning is a primary motivation for the main results in the paper, and the results as they present would be in some sense independent of the learning goal itself. Okay, so what are over-parameterized models? So there are various definitions you can come up with, but the most working definitions for this talk you can think of as this optimization problem, where I'm minimizing some form of loss over the training data set is ill-posed, in a sense that the optimization problem has many global minimizers. One way to think about it is like think of very large neural networks, like they can in principle represent any continuous function. So if in infinite width neural networks with appropriate nonlinearity can represent, if there is no other constraint, can represent any continuous function. So if you want a cartoon picture, if you have a few data points and you want to fit it with like minimize this some sort of loss over these data points, you can fit it with very many different types of continuous functions. So you can fit it with something simple as like a linear interpolation, or smooth interpolation, or something totally bizarre, which is unlikely to be good for our learning goal. So, but the key point is all of these are valid global minimizers. Both the good looking ones as well as the crazy looking ones are valid global minimizers of the optimization objective if you were to optimize over infinite width network. And this is not just a cartoon. Indeed, it is common in many deep learning practice to have very large neural networks and very large scale data set where this loss is minimized using some form of stochastic gradient descent. And we'll come back to this motivation a little bit later. But so far, what I have said is nothing new. It's like looks like a classic story of overparameterization, where if you have too many parameters, you are invariably going to overfit to the overfit to the data set. There is going to be options to overfit to the data set, and even way back, like more than 10 years back, like Peter Bartlett had these papers on like why we shouldn't just look at number of parameters, but actually like the weights of parameters is an important metric to know the capacity of the network. So in some sense, like you can achieve capacity control not just by looking at the number of parameters, but also other measures like what is the norm of the weights, or like if there is some sparsity constraint or rank constraint and so on. And there has been many follow-up like empirical work where they did show that in neural networks, if you increase the width of the network, which is in turn increasing the parameters, you don't get this classic overfitting curve where after a point you start overfitting, but you can in principle get something like the error going down as you increase the network beyond like that needed to fit any random data, and it can continue to go down. And these are observations made even back in 1986, and like there are more extensive experiments on it done by Shribro, Neshabur, and so on. And I like to put this cartoon picture because this is how Peter Bartlett likes to make fun of Nati Shribro, that these are well known from a really long time back. But what is the key point here? So the key idea is like the capacity control need not come from parameters, number of parameters. In particular, controlling the norm of weights is something which is ubiquitous in a lot of learning scenarios. The most common being explicit regularization. Minimizing with L2 regularization is probably what we learn in like the second class of machine learning or so on, right after we learn what is overparameterization. And more recently, in the context of deep neural networks, L2 regularization or some form of weight regularization in many settings, not all, has also been implicated in like many forms of implicit regularization or algorithmic regularization. This is where you have some implicit form of regularization coming from specific algorithms like gradient descent, and I'll talk a little bit more about it in the second half. And of course, there are many generalization bounds which are based on L2 norm of the parameters, which are relevant in this context. So I would like to mention that norm-based capacity control is not the only ways to do it, but today we'll focus on primarily norms and specifically L2 norm. So what are we looking at today? So we're going to be looking at what is the function space view of controlling L2 norm. So this is a picture I would like to keep in mind. So on the right-hand side is like you can think of a cartoon of the space of all the weights. So weights are tunable parameters. So I'm going to use them interchangeably. And let's say you're restricting by some explicit constraints or like by the way the gradient descent works on your landscape, you say that your final solution is going to be restricted in a small L2 norm ball. And what we are going to study is like, how does it look? How does this small L2 norm ball look if we map it to the function space? Because ultimately your prediction only depends upon what the function looks like. And so that's going to be the primary goal. And you can immediately see that like if you think about neural networks, different architectures, even if they represent the same fundamental model class, like if you think of infinite width networks, which all represent continuous functions, using different architectures, you're essentially changing this mapping between the parameter space to function space. So you will indeed get very different constraints in the function space or very different induced inductive biases in the constraint space. And we can capture what this is by what we call as like the induced regularizer, which you can just think of as the representation cost measured in terms of L2 norm of weights. So you can define this for any function independent of the data or the learning process, where for any functions and a given architecture, you're trying to see what is the minimum L2 norm in terms of weights required to fit to exactly realize that function. So you have a function over the inputs, and you're looking at a parametric class of functions, and we want to say what is the minimum L2 norm required to realize this function. And I purposefully put inf here so that I don't have to put a condition that f has to be realized by the architecture. Because if there is no parameter setting which can realize the function, you will get infinity. So this is still a valid regularizer. So does this expression make sense? So it's simply like what is the cost of representing a function? So f is a function, and you're looking at the function on the entire input space. And among all the there might be many networks or many parametric functions which can realize the same function class, and then we are looking at what is the minimum L2 norm function. Does this make sense? And of course, the most easy example is linear networks, which I'm going to come back in like the next slide, which is going to be the primary motivation of the talk. And you can immediately see that if we have a minimization problem where we are minimizing L2 norm plus some loss which only depends upon the parameters W through the function, like let's say some training loss, which only depends upon what the function is, like not what exactly the parameters are, then you can replace it, at least in terms of optimization, you can replace it as minimizing this induced regularizer subject to fitting the same loss with any general function. So this induced regularizer, although it's written with independent of the data or independent of the learning or optimization process, it is closely related to what we might expect by explicitly minimizing L2 norm in some space. So we'll be studying this for a specific architecture, and just to give a bit of a recap, so this has been like directly or indirectly specified for a bunch of different architectures in different settings. So one, I want to highlight two things from this page, which will be relevant for our talk too. So one is like, so the first three architectures are simply linear models. So the first one is like just linear fully connected networks. It's essentially a fully connected network without any non-linearity. So in the end, it's just going to represent a linear function. And the linear function is given by the weights of the first networks, weights of the second network, and so on up to n. And it's isomorphic. This can realize all possible linear functions. And in this case, you can show that the induced regularizer is also simply the L2 norm. So, and then we look at, so every such linear network realizes a linear function, and the linear function we denote by beta. So beta is going to be, if this is in RD, this beta is also going to be in RD. So set of all linear functions is isomorphic to beta in RD. And the induced regularizer in this case can be shown to be like just L2 norm of the final end-to-end linear predictor. In contrast, if you look at the third, in retrospect, I should have put it, flip the order. If you look at the third network, which is like linear full bit convolution network. So here you're putting, instead of fully connected layers, all but the last layer is going to be convolution, and the kernel size is full D. So if your inputs are in RD, your full kernel size is going to be in RD2. And in this case, you are essentially implementing your end-to-end linear function can be specified in terms of convolution. And here, the induced regularizer looks to be very different from what you get for linear predictors. Here, the induced regularizer on the end-to-end linear function is is given by the 2/L quasi-norm of the Fourier transform of beta. So DFT of beta is essentially take the Fourier transform of beta, and then you take the 2/L quasi-norm. So specifically for L equal to 2, you get an L1 norm. And if you compare it with fully connected networks, you see that just by changing the architecture, I haven't changed the underlying function class. Both architectures represent the same underlying function class of all linear functions in RD. So there is no explicitly, I'm not like constraining the model class of functions by the architecture, but minimizing L2 norm of the parameters in these two cases leads to very different induced biases or inductive biases. So if I were to run an algorithm which will guarantee me minimum L2 norm solution of the weights, in these two architectures, I'll get very different performance on the data set, or very different functions returned on the if I look at the end-to-end function. And so we will be working more with convolutions in a bit, but just to give a complete picture, this has also been studied in like in the context of matrix factorization, which is the same as two-layer linear network, but with multiple outputs, in which case your end-to-end linear map is like a matrix, and the induced regularizer can be shown to be a nuclear norm. And finally, like if you think of nonlinear networks, the primary result I know of is like this infinite width networks, where you have infinite width ReLU network with biases, where you don't regularize the biases, but just put the regularized L2 norm of the weights. In this case, for univariate functions where the input is of dimension 1, there is a nice clean form, closed form solution, which is you can realize the induced regularizer in the function space is given by the total variation norm of the second derivative, which in some sense relates to smoothness of the function. So it's kind of nice that we can explicitly write this formulation. You can also give a explicit computable formulation for larger D, but it's a bit more complex to explain, and I would not go into it. And there has been some follow-up which show that you don't really, if you're looking at specific data set, finite data sets, you don't need infinite width. You can, in fact, realize the minimum L2 norm function using finite width. And again, like these are related work, you can look up the references cited here. Okay, so today I'll be focusing on going back to linear models, specifically convolutions, and we'll be focusing on what is the induced regularizer look like for different convolution architectures, specifically focusing on multi-channel architectures. So just to give a setup for single channel, so in single channel, you have an induced regularizer. So you have a convolution network is defined as follows. So you have your input X, and for the first layer operation, you apply a convolution with what is known as a kernel. Here, the kernel I'm going to denote by U. And it's essentially, it can be of width K, and we are considering like continuous kernels, continuous and circular kernels. So there is no padding, there is no strides, there is no strides, and there is circular padding. So you're just repeating, you're thinking the input signal as repeated infinite times. And so when you reach the end of this image, you circle back. This is to make the analysis a little bit easier, but with a lot more complications, you can also analyze zero padding, but we won't go into it. And the second layer is simply just a linear combination of the input. So there is still no nonlinearity, and you are still effectively implementing a linear function. And the effective linear function implemented by this network, I'm going to denote as beta. So the parameters of the network are U and V, where U is of size K and V is of size G, and the effective end-to-end linear function. So implemented by this, I'm going to denote as beta, specifically beta UV. And the question we ask is like, what is the function space view of L2 norm, minimizing L2 norm of U and V if you want to realize a given linear function? And the first thing I want to note is like, note that as long as, even if U is just one dimensional, we can realize a linear network, because the last layer is of any linear network, because last layer just is completely independent. And if U was even one, you're essentially replacing the first layer with what is called a diagonal layer. So you're just giving, you can set all the U's to 1, and you're just passing along the signal to the second layer, and the second layer is a linear function. So you can easily see that you can realize any linear function in this space. And the key trick, which would be kind of common in our analysis, is what is called as the Fourier trick. So specifically, what we're going to do is look at this entire formulation in the Fourier domain. So Fourier domain is nice because it diagonalizes the convolution operation. What it means is that in each of these convolution operations can be written now as like essentially an element-wise product in a different basis. So the network starts looking something much simpler than convolution networks. So the idea here is like X hat is the Fourier transform of the input. U hat is still a D-dimensional Fourier transform of the kernels. and V hat is also a Fourier transform. The stars are there as a conjugate. It's more for algebra, but you can just ignore the stars conceptually, like at a high level, to understand understand the ideas, because the stars are essentially conjugates, and usually they don't there's no conceptual meaning attached to them. So here I would like to add that so we are treating the Fourier transform in D dimensions. So even though D is the dimension of the inputs, even though U can be smaller than D, like in principle, you're treating Fourier transforms in D-dimensional space. So you're essentially going to pad with zeros and then take Fourier transform in D-dimensional space. And in that case, a convolution with a K-dimensional kernel followed by a fully connected network, the effective end-to-end linear predictor in the Fourier domain can be written as U hat inner product, element-wise product V hat. This is again like the linear function in the Fourier space. If you want to bring it back to the temporal space or the signal space, you just take the inverse Fourier transform. And I'm here assuming that everyone is familiar with Fourier transform, but if you're not, just take this as a definition of Fourier transform for now, because this is one of the most fundamental results. So as long as you trust me in that this equations are right, you can follow along even without knowing Fourier transform. Okay, and what the previous results show is essentially if K is indeed D, so if the kernel size is indeed full dimensional width, then you get L1 norm in the Fourier space as the induced regularizer. So you can write the induced regularizer now in the Fourier space as minimizing U hat and V hat, because Fourier transform is also norm preserving. So minimizing L2 norm of U is the same as minimizing L2 norm of U hat. So you can just replace that here, and your constraints can be replaced. Constraints which is beta equal to U convolved with V can be replaced with beta hat equal to U hat dot V hat. And using this, you can show that if K equal to D, what happens is essentially U hat is unconstrained. It's not completely true, but it has D unconstrained parameters, and V hat also has D unconstrained parameters. And simply by using the fact that AM greater than GM, you can just split it into U hat, the ith coordinate of UI square plus VI square can be written as the absolute greater than or equal to product of the absolute values, and the product of the absolute values by the constraints is just beta hat I. So this is just a one-line proof. So this essentially gives an upper bound, but you can also show that by setting U hat to square root of beta hat I, you can get a matching lower bound. Sorry, I'm going a little bit faster on this because I want to cover a little bit more, but the proof is not very complicated. It's just 2 lines, writing AM, GM, and then coming up with a matching lower bound. It's not very complicated. But what happens when we don't have a full dimensional width? In this case, your U hat is not completely free. U hat is a D-dimensional complex number, which is derived from a K length real values. So it's just linear transform. So we are not adding any nonlinearity. So this is an ill-defined linear system. So in particular, you cannot pick U hat to be anything you want. So obviously we are not going to get L1 norm. And the extreme case of let's say U is K equal to 1. So you're just allowing one-dimensional convolution. What is one-dimensional convolution? You're just scaling you're just scaling the input by some U and then passing it along, right? And in that case, U hat is essentially you can check that if K equal to 1, then U hat is just a scale U times all ones vector. Some scalar times all ones vector, scalar with proper scaling. And if you just, so if you want to satisfy the constraint that beta hat is equal to U hat times V hat, you can immediately see that V hat has to be the direction of beta hat. So L2 norm of V hat is going to be something which is just L2 norm of beta. And the only thing you can control in U hat square is some scalar quantity, and you can match the scalar quantity to, so that you can just optimize over the scalar quantity so that it gets a minimum. And you can show that in this case, for K equal to 1, the induced regularizer indeed is something very simple, which is just a simple L2 norm, scaled L2 norm. And here you can see the contrast. As you increase K, you go from something which is completely basis independent. So L2 norm of beta is like completely, it doesn't care about Fourier domain or frequency domain or any other domain for that matter, which is important for images. And for larger and larger K, you get to something which is sparsity in a specific basis for frequency basis. In particular, L1 norm in the frequency basis doesn't mean that you get like L1 norm in any other basis, or in some sense it induces sparse regularizer in specific basis. And you can see that in if you run this experimentally too. So this is like a TAI experiment on MNIST dataset where you have you're trying to classify 0 versus 1. Like you can see that like this is a simple enough dataset that you can immediately see that like even with K equal to 1, you get something like a dominant 1 and then followed by some zeros around. And then if you look at the frequency component, it still has like some zeros, but not a lot. I think the PowerPoint is coming out more saturated than it is. It's in grayscale. So it has a lot of like small values, but not zeros, exact zeros. And for K equal to D, you get like actually minimum L1 norm solution in the frequency domain. So sorry, I should have said it before. In this picture, the top 2 pictures are for K equal to 1 and bottom 2 pictures are for K equal to D. And the top left is like the signal domain, what it looks like as a linear predictor in image space. And the right is what it looks like in the frequency space. And you can see that for K equal to D, you start to have like sparsity in the frequency domain. Like, I'm sorry, you cannot see the difference in sparsity levels. I should have put a log plot or something. But you can see it clearly in the image space, where you start seeing repeated patterns, which are indicative of frequency sparsity. And you can also argue that this is a nicer predictor for classifying 0 versus 1, because it's not so focused on. So in particular, this will be somewhat translation invariant. You can see specifically if I shift the position of 1 in my test data set by some at least like the right amount, I'll match. I'll still get some signal. Whereas in the first one, you'll just get zeros. And so you can see that at least for image processing applications, why having sparsity in the Fourier domain might be more more interesting regularizer than just L2 norm itself. So we can try to we in fact like started out this project by trying to answer what happens for a general case. And it turns out like there is no easy closed form solution in any known basis. So, so specifically, even if you go for the intermediate cases where K is not equal to 1 or D. So even if you go for K equal to 2, you start seeing that like you get a complicated polynomial minimization problem over scalars, which is unlikely to have a closed form solution in Fourier basis. I cannot say that it will never have a closed form solution in any basis, but any of the standard image bases like wavelets, like standard wavelet basis and so on, it doesn't seem to have a simple closed form solution. But of course, I cannot provably show that it will never have a closed form solution. So the hope is that we can still like say something about these regularizers in a setting, in a way that when we apply it to specific data sets, which is what we will eventually care about, like we can argue about the properties of it. So what I mean by that is like so far we have talked about this induced regularizer for any linear predictor. And usually we care about this kind of induced regularizer in the context of learning, where we want to minimize it while also fitting some data sets. And something which we don't do in our paper, and but we provide tools which is useful, is what happens if I bring in data in there. So without the data, it does look like, at least for any known standard image basis, you don't get like easy closed form solutions. And but even though we don't get closed form solutions, even for K equal to 2, you can start seeing that there is some sort of group sparsity. It's hard to convey this in like 1 minute I'm going to spend on this. But if you think about what happens inside the square root, it's like each of the beta j's are the jth coordinate in the Fourier transform. They're getting weighted by some quantity which essentially varies smoothly. So the nearby coordinates of beta hat j are going to be weighted similarly than the far away coordinates. And it's going to vary in a cyclic manner, and the cycles go from like, the cycles don't repeat. And you're picking among like, so in some sense, you are looking at different bands. This is purely speculative, and except for a few places where we can quantify it. So you're looking at a weighted average, and the weights are shared in a way that like the position of the coordinates starts becoming important. So you start to get this kind of a group structure. So nearby frequencies are weighted similarly. So if you know that so this is where, if you have a data set where there is a lot of the signal is in like the large frequency components, you will try to put this alpha weight on in such a way that you are highly underweighting the large frequency component and overweighting the low frequency components if you're minimizing over alpha. Yeah. But that's something is something of interest to study. And in fact, like we start seeing that, so yeah, here I do have the log plot and the frequency. So here are the plots for in the signal domain and the frequency domain for different values of k, starting with k equal to 1, k equal to 5, 16, and 28. So it's going from top to bottom, left to right. And the right-hand side of each pair is the frequency component, but now in log scale. And here you can see that like for k equal to 2, k equal to 1, you don't have much sparsity in the special sparsity in the frequency domain. But even for small values of k, like k equal to 5, you can even, in the paper, we also have for k equal to 3, which is the standard formulation used. You start seeing some sparsity, but the sparsity is more like group. Like whenever there is a white region, the white regions are combined together. And as you increase the k more and more, it tends to go towards sparse regularizers more than group sparse regularizers. So this is more an empirical observation on this problem. So what are the tools we can develop still in this setting? So one of the main contributions of our paper is to come up with this SDP relaxation. So we start with this basic initial problem, and I can now replace inf with min because we just argued a while back that every linear predictor is realizable by even a small network, by even a k equal to 1 network. And if we now look at like what are the objectives and constraints of this optimization problem. So you look at the objective, it's L2 norm of u plus L2 norm of v. It's also equal to L2 norm of u hat plus v hat because it's Fourier transform as energy preserving. And you can write it as trace of UU transpose plus VV transpose. So if you create a matrix UU transpose plus VV transpose, you can just write the objective in terms of those two matrices. And moreover, if you look at the constraints, you can write the constraints in terms of UV transpose matrix. So you can see that both the objective and constraints can be written in terms of this lifted matrix. So I construct this lifted matrix, which consists of U and V and U and V transpose. So it consists of 4 blocks: UU transpose, UV transpose, VU transpose, VV transpose. And then I can just take linear combination of these lifted matrices, linear. So you can write both the objective and the constraint so far as a linear function of W, right? But there is a catch, which is that like W is not completely unconstrained. So as I have written, like W has to be rank 1. Right? So as long as if I give you a W which is rank 1, which minimizes the objective and gives you the constraint, you know that like you have got to the optimum solution. So you can write this optimization problem exactly as follows, where you minimize over W, which is PSD. So W, the way I've written it, will be PSD. W, which is PSD. You minimize the trace subject to some linear constraints such that it will be satisfied, and you have a rank 1 constraint. Rank 1 constraint comes from the fact that U and V are just vectors. And you can immediately see what will be the SDP relaxation. SDP relaxation is going to be like just dropping the rank constraint. And this gives you a simple SDP. And you can immediately see that like just from this one formulation, you can at least create very quick, very easy to compute upper bounds on the, lower bounds on this objective. And so moreover, like this SDP relaxation also naturally extends for case of multi-channel output. So here we are considering multi-output channels. So it's a little bit more complicated network where you do the same operation, like convolution operation, but multiple times. So from your input, you apply U1 to get one channel of convolutions, U2 to get another channel, U3 to get another channel, And the second layer is still nonlinear and then just takes the linear combination of all the inputs. So the dotted lines represent convolution, this cartoon, and solid lines represent just linear combination or fully connected version. And exact mathematical formula is here. And here what you can show is that, sorry, I'm going to minimize. Yeah. So what you can show is that like beta hat, which is like it is still a linear function. So it still implements a linear end-to-end model. So now the beta hat, which is like a linear combination, can still be written in terms of U hat and V hat. In fact, like now U and V are matrices. So I change. So U is like K times C out, where C out is a number of output channels. And so you're like, each column of U represents like one of the filters for that particular output channel. And V out is like the corresponding linear predictor for the outputs of the channel. And now you can see that the diagonal, U hat, beta hat can be written in terms of, the objective can still be written in terms of U hat and V hat in a simple form where you construct U hat, V hat transpose. Actually, like the way I've defined V hat, V here, it will just be U hat, V hat. And so you can, by similar argument, the way I derived the SDP in the previous case, you can again construct W, which is essentially by stacking UV and then UV transpose. So one other thing I forgot to mention is that U hat is nothing but the Fourier matrix applied to U. So each column gets its own Fourier transform. And V hat is again like each column, I should just swap we consider V to be D times C out, and then each column gets its own Fourier transform, D-dimensional Fourier transform. So now for multi-channel inputs, the induced regularizer can be written. Now again, we can define an induced regularizer as what happens when you minimize L2 norm. And for multi-channel outputs, you can again write it as what looks like an SDP with rank constraint, where rank is less than or equal to C out. And you can again like write an SDP relaxation by just dropping C out. And now just simply staring at these two relaxations, you see that once C out is greater than like whatever K plus D, W is of size K plus D times K plus D. So once C out is greater than K plus D, where K is the size of the kernel size and D is the input dimension, just by definition, like it will stop mattering. Like the number of output channels will not affect the induced regularizer at all. But in fact, like what we show is that very strong result, which is saying that it doesn't matter. You don't want C out to be that high. You can, for any C out, the induced regularizer doesn't matter. So just to drive the point home, like I said, now you're getting a more complex network where you have multiple channels and the number of channels can be any numbers. And I'm saying that so in principle, if I'm getting minimum L2 norm, I can just spread it anyway across these channels. But if I look at it in the function space, the induced regularizer is completely independent of C outs. So because you can show SDP, which is independent of C out, is tight for all values of C out. And in particular, the main corollary of this theorem is that if I'm looking at minimum L2 norm solutions, it doesn't matter what is the number of output channels are. You're at least for linear networks, you're going to get the same induced, same predictor. And in particular, for any output channel, you get because it's an SDP, the induced regularizer we show is equivalent to an SDP. It is also a norm. And specifically, it's a norm which interpolates between L2 norm of the predictor, which is just basis independent, to L1 norm specifically in the Fourier space. So this is another structure which comes out of just knowing that the induced regularizer is a convex function which can be expressed as an SDP. And in fact, like by manipulating this SDP, you can also get bounds on when it is closer to what values of K it's closer to L2 norm versus L1 norm, but a lot more can be done with just using the SDP. Just a few comments on the proof. So like I said, just by looking at definition, you can show that the SDP is tight when C out is greater than D plus K. D is the dimension and K is the kernel size. But if you do a little bit more work, like just look at the KKT conditions, which is the first order optimality conditions of the SDP, you can show that every solution of the SDP is of rank K. So upon showing that going D plus K is like just definitional, showing tightness for up to K is still very easy. You just need to do a few more steps. But the tricky part is like showing tightness for any K. So it's specifically showing that for any C out, your induced regularizer is independent of C out is going to be much tricky. In fact, we never construct such. So the way to do it would be to show that there exists a solution of this SGP, which is of rank 1. And once we show that there exists an optimum solution, which is of rank 1, we are done. And in principle, that doesn't mean that all the solutions of the SGP are rank 1. In particular, this SGP can have multiple solutions in higher dimensional space. But showing that there exists a rank 1 optimum will show that the SGP is tight, like the cost you pay is the same. In fact, we never construct this rank 1 solution. We only implicitly show the existence of this rank 1 solution from any solution of SGP. So given an SGP, we use the polynomial representation of convolutions to reason about like the fact that like any solution of the SGP can be represented as a rank 1 solution. And in where like neither the objective nor the constraints change. And a key lemma, which might be of independent interest, which I'm going to just briefly mention, is showing that for a star represents the convolution operation for any A, B, and C. For any A, B vectors in RK, you can write A convolved with B plus B convolved with B as like just one vector convolved with itself. I don't know if this is a known result in signal processing. We tried to look it up, but we couldn't find anything. But there is a implicit existence proof for this result in our paper, which might be of interest. So, so this is our primary result for multiple output channel networks. So I don't have too much time to go into multiple input channel networks, but briefly in our paper we also look at what happens when you have multiple input channels. So you can think of the inputs as RGB channels and like color channels in the context of image processing. And so now you have like again different convolutions in the first layer, where for each input to each output there is a convolution. And so the number of convolutions you are doing is like number of input channels times number of output channels. And here the end-to-end network you're implementing is a matrix, because your inputs is a matrix. You can think of the inputs as D times C in matrix. So your end-to-end linear network will also be a matrix. And here we can you can again write it as you look at the problem in the Fourier domain, and you can write an SGP relaxation, but this SGP relaxation, unlike the single channel case, is not always tight. But we can show conditions under which it is tight. Like it's, in fact, you can prove that it is never necessarily tight, mainly because you can provably show that multiple output channels may even be necessary to even realize all linear functions. Forget like what is the representation cost. If I look at if I don't have multiple output channels, I may not even realize all matrices which map inputs to output. So in order to realize, like, you still need like multiple output channels. That means the representation cost will depend on the multiple output channels. One conjecture is that like once you can realize all linear models, the representation cost is independent of the number of output channels, but we show a loser case where we show tightness. In particular, you can show that in order to realize, I don't have it in the slides, in order to realize all linear networks, you only need the number of output channels to be greater than D by K. And we conjecture that is sufficient, but it's not clear that we didn't prove it. In fact, we proved it for a loser value of C out. But again, like in special cases, we can show tightness for appropriate values of C out. And in fact, like this will be optimal. And here, the interesting part is like these closed forms again show some interesting structures. So for K equal to 1, you can show that when C out is greater than the number of input channels, the end-to-end linear function represented is in fact is going to be is going to have a induced regularizer, which is the minimum nuclear norm. And this is this in comparison for single input channels where you get minimum L2 norm. So it's interesting that it still tries to give a structure among the input channels, but it's again basis independent. So the nuclear norm, if you transform it by Fourier matrix or any other unitary matrix, it's still remains the same. So this doesn't give special structure in any special basis. But on the other hand, for k equal to d, we can show that for any cout here, we don't need, when k is large enough, we don't need multiple output channels. And here you can show that you get a group sparse structure in the Fourier space. What it means is that you get an L1 norm in the Fourier across Fourier frequency components, but L2 norm across the channel. So you map the entire end-to-end matrix to Fourier domain, and then you take L2 norm of each component along the channels and L1 norm of those L2 norms. So this is an interesting property on how you get structure across channels. Okay, so I'm kind of a little bit over time, and I wanted to make connections to gradient descent and show some experimental results. But before I go into it, I was just wondering if there are any questions I can answer at this point. Okay. If there are no questions, I'm going to go ahead and finish my presentation, if that's okay. Okay. So I talked a lot about this induced regularizer and say that how it actually even for linear networks, which we think we understand, where we can actually solve this minimum L2 norm solution exactly by massaging it a little bit, we get very interesting regularizers. So in particular, it's interesting that you get structure in the frequency domain even without nonlinearity, and the structure behaves something intuitively as we add number of input channels, because once we add number of input channels, we are going to be looking for same frequency in a different. For example, if you have RGB channels, we want to look for same frequency component in different RGB channels. And it's also interesting that smaller Ks still have some kind of sparsity in the frequency domain, but it looks a bit more complicated and looks more group sparse or band pass filtering kind of a structure. But where does it fit in terms of learning process, which is our primary motivation? I will defend that this question is independent just as a representation cost, as an exercise in understanding what the function space view is. But just to connect it to learning, which is one of the primary motivations, I'll talk a little bit about implicit regularization, or implicit capacity control, algorithmic regularization from gradient descent. So just to go back to this cartoon picture I started in the beginning, in over-parameterized models, there are usually multiple global minimizers. And although in practice, deep neural networks, we use some kind of a regularization, we can never ensure that the regularization is effective, because these are all non-convex problems, and you can never say that you go to the minimum L2 norm solution. And in fact, some experimental studies have shown that even when you add the standard regularizations used in practice for convolution networks, the capacity is still large enough that once you run gradient descent for long enough number of iterations, you get you get to fit even random labels. That means it's not just fitting the data, but it can fit you overfit to some crazy labels too, particularly adversarial labels. So just to be clear, the explicit regularizations considered, which are usually dropout and weight decay, are not exactly equal to writing some form of minimum L2 norm, but they're somewhat related. But the high level point is these explicit regularization techniques are not sufficient to enforce capacity control. And it is by now well understood that algorithmic choices actually play an important role in terms of where the real capacity control or real inductive bias comes from. So here by algorithmic choices is what are the, how we do the optimization over this landscape matters very much. And so the optimization algorithm, which is typically based on some form of geometry, is key to this this idea. And the cartoon picture to keep in mind is you have a complicated landscape, and with a lot of global minimizers, and depending upon which path you take, your algorithm takes, you end up in different global minimizers. And what is the next step you take is dependent on the specific algorithm. Gradient descent will go in terms of steepest direction in L2 norm, coordinate descent will go in terms of the steepest direction in L1 norm, and so on. So you see that different choices of optimization algorithms do indeed lead to different solutions. But whenever I give this pitch, I've always heard that, but don't we always use just SGD? Like we can analyze different algorithms, but you almost always just use SGD. Why don't we just see what is the analysis of gradient descent? That's a fair point. But even within SGD, like there is a lot of other factors which influence the final induced bias. And two key components among them are network architectures. So if you think of gradient descent just looks at a small ball around your current point, goes in the direction of minimum L2 norm in the parameters. But like we saw, going in the direction of minimum L2 norm might mean that you go in for different architectures. You might go in very different geometries. You might trace very different trajectories in the function space, depending upon the architecture. And we saw some examples today. So understanding how this geometry of like gradient descent looks in the function space is kind of very interesting. And so the other thing I won't talk about, but I also have some work on it is hyperparameters like initialization, step size, and all of these also affect what is the trajectory you take. And usually having good analysis, which is encompassing of all these parameters, is much harder. And these system trajectories get very complicated very quickly. But one result I would highlight, which also motivates why we looked at L2 norm, you can just think of an L2 norm as an important regularizer, because gradient descent does local L2 regularization. But gradient descent also has this connection to L2 norm through a global setting, where if you think, so consider this problem of loss minimization over what we call as homogeneous models. What it means is like if you scale the parameters by alpha and your function essentially gets scaled by the same parameter, a positive parameter alpha, your function gets scaled by the some function, just a scalar quantity, doesn't change direction. And we are going to use strictly decaying losses like logistic loss. Why logistic loss is important is it gives us an asymptotic regime where analysis is much simpler. Like I said, if you go non-asymptotic regimes, these analyses get very complicated. But logistic loss is like a technical convenience, which gives us an asymptotic regime where the analysis is simpler. The idea is that if you do logistic loss on a separable data set, the easiest to keep in mind is linearly separable data set. It never really converges. It diverges, in fact. Like you have to keep increasing the norm of W to make it go to zero. It never reaches zero. It only reaches zero asymptotically as the norm of W goes to infinity. And so we can look at the asymptotic of what happens when the norm of W does go to infinity. So for homogeneous models, you only care about the direction. You don't care what the norm is. So if you're thinking of linear classifiers, you only care about what is the angle of the linear classifier. So you can ask what is the direction convergent. And this theorem, which is motivating for L2 norm, is essentially says it's built upon a lot of previous work, but this is the most state-of-the-art result, which says that if you are looking at homogeneous model, which includes linear models as well as ReLU networks without skip connections, and if you're looking at if you're driving using gradient descent to drive the logistic loss to zero. In particular, you can show that once you classify the data correctly, gradient descent will converge to zero if you run it for infinite time, and with appropriate subsize, of course. And so in that case, you can show that the direction of parameters, which is W of t normalized by L2 norms, just looking at the direction, that converges along something which is related to minimizing L2 norm. So what the theorem exactly says that you converge to KKT points of this problem, and but you can see that the L2 norm plays an important role here. And so this is one of the primary motivations for us studying L2 norm in the function space. So if we were to believe this theorem, this has some caveats which I'll mention in a slide, but if we were to believe this theorem, L2 norm of the parameters is the primary inductive bias we are getting from it, implicit inductive bias we are getting from gradient descent. And it makes sense to study L2 norm, what is the effect in the function space. But just to give a cautionary tale, this is not a complete picture. I don't want to give an impression that we have solved this. We know that gradient descent minimizes L2 norm. One primary caveat is that I never, like I said, these two functions are equivalent only in global minimizers. But the theorem itself says that you only converge to stationary points of the first optimization problem, which may be completely independent of the stationary points of the second optimization problem. So there is a connection, but the connection is not like always correct. And further, I said, it's asymptotic results. There has been like explicit proofs where in the non-asymptotic regimes and different loss functions, you don't get norm minimization. But norm minimization does occur enough number of times that it makes it a motivating example. And a historical anecdote, because it's a stat seminar, is like a connection between Lars and Lasso. It is never exact. Like if you're familiar with the forward stage-wise feature correction, there was a lot of work on connecting it to explicitly L1 minimization, but it was never exact. But it was reasonable. It was reasonable in many problems that it was of interest independently. But what we can say is that any theory results we provide, we can actually like now try to see what happens empirically. Now we don't say anything. Our theoretical results I presented today doesn't say anything about gradient descent. It doesn't say anything about learning on a specific data set. But it gives us a closed form convex regularizer that we can actually run it on specific data set and see if the theoretical results hold true. And I'll just conclude with like 2 slides of experimental results where I'm going to essentially say that the theorems work when we run gradient descent on MNIST dataset. So that's the thing where we run gradient descent on MNIST dataset, and although our theory doesn't say anything about gradient descent, you can see that like the resulting solutions are indeed independent of the number of channels. So this is visually, and this is more quantitatively when you run gradient descent. And there are some numerical errors, but usually if you run gradient descent long enough, those numerical errors go away. And most interestingly, even though our theorem is only for linear networks, we observe this behavior when we run it on like networks with non-linearity. But this, of course, requires a little more experiments to say anything quantitative, because you are estimating what RK of C is by looking at L2 norm of the weights. And we see that the final L2 norm you converge to is indeed independent of like C even for any non-linearity. And this essentially is like an example where you can take heuristics from simpler model and actually try experimental stuff on non-linear model. I apologize for going over time, and just put summary slide recapping the stuff I talked about, but primarily I told you about the nature of induced regularizer for multi-channel and convolution networks. And for single channel, the main results showed that you are independent of the number of output channels. And for multiple channels, you see that the number of input channels matter, at least like a minimum number is required. And in most of our experiments, we see that after that it stops mattering, but the analysis is not completely tied there, and we provide some experiments. Thank you for your attention. I apologize for going over time.
Thank you very much. That was great.